So let's go on to classification of second order PDEs. So that is C. Classification of second order partial differential equations. Or types of second order, maybe I should rather write it types of partial, types of, the classification will fall under a different. So types of second order partial differential equation. The first one is what we have, what we call the wave or the vibrating string, the wave equation. The first one is what we call the wave equation. The wave equation in one dimension is given by this, the squared u over the t squared is equal to c squared, the squared u over the s squared. Okay, so we have the wave or the vibrating string. The wave equation. The wave equation in 2D takes this form. The squared u over the t squared is equal to c squared, a bracket, the squared u over the x squared, different variables. So that is why we have 2D here. Two different variables, that's why we have 2D here. One variable, that is why we have 1D here. So the t will be fixed at all costs. Okay. Now what about if I tell you to write the wave equation in n dimension? It's going to be the squared u over the t squared is equal to c squared. Then you have the squared u over the x1, the squared u over the x2, all square up to the squared u over the xn squared. This is the wave equation in n dimension. When I say n dimension, I can't say the x dy because the x dy dz, the variables are finished. So I rather use x1, x2, etc. Okay, so this is the wave equation. The second one is what we call the heat or the diffusion equation. The heat or the diffusion equation. We can also have a one-dimension form for that. And the heat or the diffusion equation is given by this. The squared u over, the u over the t is equal to c squared, the squared u over the s squared. Look at the one dimension for the heat diffusion equation and the one dimension for the wave. For the wave equation, both left and right hand side are second order, but for the heat equation, the u dt is only of first order. So a second order, a 2D form will be the u over the t, c squared, the squared u over the s squared, plus the squared u over the y squared. This should be a 2D, etc., etc., etc. C squared is what we call the thermal diffusivity. Sometimes they call it K, we call it thermal diffusivity. Thermal diffusivity. Then we have 3. The third one is what we call the Laplace equation. So Laplace is appearing almost everywhere. Laplace equation. We also have Laplace equation in one dimension, Laplace equation in 2 dimension. But I think let's start with the 2 dimension. The 2 dimension for the Laplace equation is this. This is the Laplace equation for the 2 dimension. This is Laplace equation for 2 dimension. So Laplace equation here is 0. Okay. You may have read this in engineering maths 1, where I used to call this Laplacian. Laplacian is equal to 0, or the Hamiltonian. This is Laplacian, and this is normally called the Hamiltonian. Okay, they are the same. Then, so what about Laplace in 3 dimensions? Laplace in 3 dimensions will be the squared u over the s squared, the squared u over the y squared, the squared u over the z squared is equal to 0. The Laplace have interesting properties here, all equals 0. Then let's move on to 4, what we call the Poisson Poisson equation. Poisson equation. Let's discuss Poisson equation in 2 dimensions. Poisson equation looks like the Laplace equation, just that it is not equal to 0. This is the Poisson equation in 2 dimensions. This is the dimension, the 2 dimension x, y. So in 3 dimensions, the Poisson is going to be this. Is equal to x, y, z. This is the Poisson equation in 3 dimensions. Let's look at the format. In an example, I'm supposed to ask a person like this. You must know the name and the equation. I can write the name and I'll tell you to write the equation. Or I can write the equation and tell you to write the name. Okay, so note it carefully. Let's move on to what we call the Helmholtz. I can also write this in a nice way. I can write this in a nice way as this. I can write it because this is the same as the Laplacian. I can write it. Okay, let's go to the next one. The next one, this is 1, 2, 3, 4. So the next one, the 5th one is Helmholtz equation. Helmholtz equation. Now the Helmholtz equation is given by this. Or better still, this is 2 dimensions. So better still, you have this plus this plus this is equal to 0. This is the Helmholtz equation. Either this or this. Of course, I expect you to know that this is the same as this. And we call this V is non-dimensional velocity. Velocity without dimension. Non-dimensional velocity. So this is careful. Then there's a 6th one. I'll let you go and look for it. Then I'll write a 7th one for you. The 6th one, Schrodinger's equation. Schrodinger's equation. It is normally found in quantum mechanics. Schrodinger's equation. Okay, so you go and look for Schrodinger's equation. I'll write the next one. That's the transmission line before we go on. Okay. So the 7th one is a transmission to everyone. Transmission lines. There are 2 types of transmission lines. We have the radio lines, and we have telegraph or telephone lines. You know, the radio lines are different. You know, the radio lines are when we phone into a radio station, they have their own lines. And the telegraph or we have also telephone lines. There are 2 different things. Look at the radio. We have the radio lines. For the radio lines, in the 2nd order is given as d squared u over dx squared equals LC d squared V over dt squared. Then there's a 2nd one, d squared I over dt squared. This is u. Yeah. The radio lines make use of capacitance and inductance. So notice carefully. The radio lines make use of capacitance and inductance. And both left and right hand side are all 2nd order. Compare it with the other line, telegraph. Telegraph equations. This one I should have written radio equations, or else the radio lines, they are the same, radio lines. But normally they write radio equations. Okay, radio equation. Now the telegraph equations, we have d squared V over dx squared is equal to kc dv over dt, du over dt. This time it's not even k, it is rc. This is capacitance, but this is resistance. So you could see that this and this are a little bit different. This and this are a little bit different. The telegraph makes use of resistance. The radio makes use of inductance. The other one is the squared I over dx squared is equal to rc di over dt. So these are the transmission lines. Then you have this line, and you have the radio lines, and you have the telegraph lines. Okay, so this is the telegraph equations. we will move on to, but note carefully for the telegraph equation. So note, if I have y squared partial x, it will give me y squared out partial x, because with respect to x, there's no x here, so this will come out as this. Then now when I integrate this, this and this will give me x. The constant for this will be f of y. Let us note something interesting here. Assuming I'm integrating f of x partial x. Assuming I'm integrating f of x partial x. I'm going to get, let's say small letter f. I'm going to get capital f of x plus g of a different variable. Because this is with respect to x, that constant will be a function of y. Why f of x small letter, why capital F of x? Why this and that? Look at this example. If I integrate anything in x, if I integrate anything in x, my answer is still going to be in x. Anything that I integrate in x, I'm going to get an answer that belongs to the same family. There's no way you integrate x and go and get y family. If you integrate something in x, you're going to get an answer in x. If you integrate sine y, you're going to get something in y. So if I integrate small f of x dx, I'm supposed to get an answer which is another function f of x before that. So especially not the constant for partial integration. That is what is going to guide us in our next subtopic.